Welcome. In this lecture, we will discuss conduction, convection, radiation, Newton's law of cooling, and the greenhouse effect. Heat transfer. Heat transfer is the exchange of thermal energy between physical systems. There are three modes of heat transfer: conduction, convection, and radiation, and we will discuss these three in the order shown here, going from left to right. Conduction is the transfer of energy by microscopic collisions of particles within a body while in direct contact with another body or source. For example, when the end of an iron rod is held in a flame, the atoms at the heated end vibrate more rapidly. These atoms vibrate against neighboring atoms, freeing electrons that can drift through the metal, transferring energy by colliding with atoms and other electrons. Consider two materials, metal and wood. If you were to touch both of these with your hand, which one feels colder? Which one is colder? Well, we know, because of our definition of temperature that we defined in the previous chapter, temperature is just the average kinetic energy, or at least it's related to the average kinetic energy. If I have both these materials, a piece of metal and a piece of wood, sitting in a room, both of those would reach thermal equilibrium with the room eventually. So if I were to touch each of these materials, while each of them is at thermal equilibrium with the room, which one feels colder? Well, the metal is going to feel colder, but which one is colder? Neither is colder. They're both at the same temperature. But the metal feels colder because it is a better conductor, whereas the wood is a poor conductor, so it does not feel cold. This just means that our sensation of what is hot and what is cold is, yes, it's related to the temperature of whatever we are in contact with, but more directly, it is related to how quickly energy transfers out of us or into us. So if energy transfers out of me very quickly, I will sense something is cold. If energy transfers into me very quickly, I would sense that as being very hot. Now, that could correspond to the temperature being cold or hot, respectively, but it is also related to how rapidly energy is transferred. So a good conductor, which transfers energy better, will feel colder than a poor conductor because it doesn't transfer energy either in or out as quickly. So a conductor, as we've already discussed, is simply a material that conducts thermal energy well, and is due to its outer electrons. And because metals have the loosest outer electrons, they are the best conductors of heat and electricity. Silver is actually the best conductor, followed by copper and gold, but other materials that aren't metal can also be good conductors of thermal energy. The tile floor feels cold to the bare feet, while the carpet, which is at the same temperature, feels warm. This is because tile is a better conductor than carpet, so it more readily transfers energy from your feet into itself. The bodily sensations of hot and cold, as I mentioned already, are more accurately sensations communicating to us how quickly we are losing energy to our surroundings. So a good conductor conducts heat, obviously by the name. Conversely, a material that does not conduct well is, unsurprisingly, called an insulator, and is simply a material that does not conduct thermal energy well. And one of the materials that we already have come across is wood. But there are other materials like wool, or straw, or cork. Unlike the electrons in metals, the outer electrons in the atoms of insulators are firmly attached to the atom. They are not loose. Because wood is a good insulator, for example, it is used in the handles of cooking equipment. Even when wood is hot, it can be quickly grabbed and moved without the fear of the user being burned. Although the temperature of the wood may be high, relatively little thermal energy is conducted from the wood into the hand of the user. This is simply due to the low conductivity of wood. Now, generally, materials that have gaps or holes for gases like air are often good insulators. A warm blanket does not provide you with thermal energy. It simply slows the transfer of your body's thermal energy to the surrounding. It traps that warm air that is warmed by your body's radiant energy, in a little cocoon around you, so to speak. And so a good blanket will just keep that energy inside of it, rather than letting it escape through it. Like you wouldn't put on or cover yourself with a sheet of aluminum as your blanket. Next is convection. Convection is the transfer of thermal energy by macroscopic movement of particles. Now, conduction, which we just finished discussing, was the transfer of thermal energy by microscopic movement of particles. Here, we're discussing the macroscopic movement of particles and how energy is transferred in that way. So we can see this as energy being transferred by quote-unquote blobs of matter, as opposed to individual small constituents of matter. We look at entire blobs. So liquids and gases transmit thermal energy mainly by convection. For example, convection ovens are simply ovens with a fan inside which speeds up cooking by circulating the warm air. So convection currents transfer thermal energy in air. So it's the macroscopic movement of large blobs of matter. And we see this in the example here with a heater in some sort of room, though it's a poor illustration, I think. Another example is on the stove. The water macroscopically begins to move, carrying energy from the bottom, which is where the water is in contact with the pan, which is in direct contact with the flame. The energy transferred through the pan to the water at the bottom, and that water at the bottom heats up and then rises and then makes space for the colder water at the top to fall down, and then you create this circulating current. Or perhaps we should simply say a convection current. Consider holding a test tube filled with cold water in your hand, and you wedge chunks of ice at the bottom with some steel wool to hold it there. Then you heat the top part of the tube in a flame until the water boils. The fact that ice doesn't melt in this scenario indicates glass and water are poor conductors of thermal energy, and that convection does not move the hot water down. And you can try this at home. It's not very dangerous, and you'll see that you can have all three phases of water inside a single test tube. Convection currents stirring the atmosphere produce winds. Some parts of Earth's surface, due to having different specific heat capacities, change temperature more readily than others when exposed to the same amount of energy. The uneven temperatures produced across the Earth cause, therefore, the uneven heating of the air near the surface, which produces convection currents. For example, during the day, the land is warmer than the water, and a sea breeze results directed from the sea into the land. At night, the land is cooler than the water, so the air flows in the other direction. This, of course, is a simplification, but I hope the basic idea is conveyed. Another thing to note, which causes the air to fall back down again, is that when air rises, it expands and cools, causing it to fall back down. Problem 1. You can hold your fingers beside the candle flame without harm, but not above the flame. Why is that? Well, the answer is that thermal energy travels up by convection. Air is a poor conductor, so very little heat travels sideways. But what little thermal energy does travel sideways is due mostly to radiation. Radiation is energy carried by electromagnetic waves, such as radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. As we go from top to bottom, we are increasing the frequency of the oscillation of these waves. By increasing the frequency, we are decreasing the wavelength. But what I want you to take away here is that as you go from top to bottom in this list, with the increasing frequency comes increasing energy, where E being the energy of the wave is equal to Planck's constant, which is h multiplied by the frequency. Now we will not get into a discussion of this, but this is a simple equation that you can reference later. Future chapters talk more about waves and also about electromagnetic radiation, or electricity and magnetism generally. For this lecture, I will simply give an example of the relationship between energy and the frequency and wavelength, and we will do so by considering a wave on a rope or a wave on a string. And you can imagine using a battle rope, I think that's what they're called, at the gym. The more energy you put into the rope, the higher the frequency is, but the shorter the wavelength. So the more vigorously you pull that thing up and down, you're using more energy, the harder you do that. And of course, the more you do it, the more energy you put in, the more rapidly the oscillations are in the rope. So you see that energy is related to the frequency, and therefore it's also related to the wavelength. You can see in the upper example, when you're putting very little energy in, the frequency of the oscillations is low and the wavelength is long or large. But in the lower example, you see more rapid transverse motion. You're putting more energy into that rope and the frequency is therefore higher and the wavelength is shorter. So the length from peak to peak, or the distance from one peak to the next, is shorter. So what you should take away is that energy increases with increasing frequency, and energy increases then with decreasing wavelength. And we can use some simple illustrations of electromagnetic waves to give you a feel for the different energies. For example, radio waves, low energy waves, infrared waves, a little bit higher energy waves, and then visible light waves. So of these three, the visible light waves have the highest energy because they have the highest frequency and the shortest wavelength. If you sit by a fireplace, most of the thermal energy you receive is in the form of radiation, particularly infrared radiation. Convection carries most of the thermal energy up the chimney, and conduction does almost nothing since air is not a conductor, it's not conductive, hence the energy you receive is from electromagnetic radiation, again, infrared radiation in this particular case, at least mostly. All substances of any temperature above absolute zero emit some degree of radiation. The peak frequency of the radiant energy, aka the electromagnetic waves, is directly proportional to the temperature, as measured in Kelvin, of the object. So let's plot radiation intensity versus frequency. And let's just talk about some examples. Let's say we have an object that is at 1600 Kelvin. This would be a plot of the intensity of the radiation versus the frequency. And here we're talking about the intensity of emitted radiation, not reflected radiation, just how much an object itself gives off. If you were to put that object in a dark room, would you see it light up, for example, on its own? So some object at 1600 Kelvin emits a frequency or an intensity curve as shown here, where the peak frequency is some value here, where peak is represented by this little line over the top of the letter F, so peak frequency. If I increase the temperature, the peak frequency also increases. So let's get to an even higher temperature, and these peak frequencies get higher and higher, but these objects, whatever they are, the objects corresponding to 1600 Kelvin, 2400 Kelvin, 3200 Kelvin, are emitting some electromagnetic radiation, but they're still not hot enough for us to see it with our eyes. Unlike the sun, which is so hot that the energy it emits is in the visible light spectrum. The higher the temperature is of an object, the higher the peak frequency of emitted radiation is. Because of the sun's high temperature, it emits radiation in the visible light spectrum. Radiant energy emitted by stars is often called stellar radiation. The Earth is at a lower temperature, so it emits radiation in the infrared light spectrum, which is below our threshold of sight, so we can't actually see it with the naked eye. Radiant energy emitted by Earth is called terrestrial radiation. Both the sun and the Earth glow, but at different frequencies. This idea is the same for every object. If you look around you, every object is glowing, but everyday objects that we see emit a radiation at too low a frequency to be seen with the human eye. And again, I'm not talking about reflected light, like light hitting an object and bouncing off. I'm talking about if you set an object into a dark room, it is glowing, but is it hot enough to glow so that you can see it? Like if you put, let's say we take the sun and we throw it in a closet, a dark closet. Well, the closet's not going to be dark anymore because the sun itself is emitting visible light. It's so hot that it alone produces visible light to emit. Whereas the Earth, if you could just shove the Earth in a closet, close the door, the Earth would not be emitting any sort of light that you could see. The way we see things on Earth is by reflected light. The energy from the sun comes to Earth, reflects off of everything into our eyes, and that is how we see. I hope that distinction is clear. So consider a chunk of material. Electromagnetic radiation is incident upon the material, so part of that energy is then, after the incident energy collides with the material, part of that energy is reflected, and part of that energy is absorbed. The absorbed energy is taken by the material and then re-emitted, often at a different frequency than the incident radiation. Keeping this picture in mind, we see that absorption and reflection are opposite processes. Absorption is the material's act of taking energy into itself, whereas reflection is the material's act of shielding itself from taking energy. Most materials partly absorb and partly reflect. As you expect, a good absorber of radiant energy reflects very little energy. In the context of visible light, a surface that reflects very little light looks dark, since it absorbs visible light. The pupil of the eye, for example, allows light to enter and appears almost completely black, meaning it absorbs more than it reflects. Conversely, a surface that reflects a lot more radiant energy appears lighter. Good absorbers are also good emitters, so keep that in mind and refer back to the previous slide's picture if you need to remind yourself what the difference is between absorption, reflection, and emission. Problem 2. If a good absorber of radiant energy were a poor emitter, its temperature compared with its surroundings would be A. Lower, B. Higher, C. Unaffected, D. None of the above. The answer, of course, is higher. And the explanation is that if a good absorber were not also a good emitter, there would be a net absorption of radiant energy, and the temperature of a good absorber would continuously get hotter, all the way up to infinite temperature. But we know that nature does not behave this way. Newton's law of cooling. The rate of cooling of an object is approximately proportional to the temperature difference between the object and its environment. Mathematically, we see it written as shown here. This simply means that the bigger the difference in temperature between an object and its environment, the faster the object will change temperature. Now, I don't expect you to understand this equation or know how to do anything with it. All I want you to take away is that, well, what I already mentioned, that the bigger difference in temperature that exists between an object and its environment, the faster the object will change temperature. For example, frozen food will warm up faster in a warm room than in a cold room. And I also want to note that Newton's law of cooling is an empirical relationship and is not a fundamental law like Newton's laws of motion. So these are not in the same category. The greenhouse effect. Earth's temperature depends on the energy balance between incoming solar radiation and outgoing terrestrial radiation. The Earth's atmosphere acts as a sort of semi-permeable membrane. It allows the high-energy visible electromagnetic waves to move in and out through it, but the atmosphere does not allow low-frequency waves emitted by the Earth to easily leave. They get stuck, bouncing between the Earth's surface and the atmosphere, as shown in this illustration. Now, if this were not the case, the side of the Earth exposed to direct sunlight would be extremely hot, but the side of the Earth not exposed to the sun would become extremely cold. Life would not be possible between those two extremes. Because of the difficulty the lower frequency waves face in escaping into space, the Earth holds onto that energy and can maintain a much more consistent temperature. Now, this effect can be artificially created as well, like in a greenhouse. The sun's temperature is very high, meaning it emits electromagnetic waves of high frequency and low frequency. Those high frequency waves pass easily through the green glass of a greenhouse, just as they easily pass through the Earth's atmosphere. Those waves are then absorbed by the plants inside the greenhouse, and the plants then emit their own electromagnetic radiation, but because the plants are at a much lower temperature than the sun, their emitted electromagnetic waves have lower frequency and high wavelength, which cannot pass through the green glass of the greenhouse, but instead get reflected back to the plants, keeping that whole enclosure at a relatively constant temperature. Summary. We discussed conduction, convection, radiation, Newton's law of cooling, and the greenhouse effect. I'll see you next time.